Okay, today I'm doing question 5, and it says a fish swimming in a horizontal plane has initial velocity equal to 4I plus 1j meters per second at a point in the ocean where the position relative to a certain rock is a vector r initial is equal to 10I minus 4j meters. After the fish swims with constant acceleration for 20 seconds, its velocity is vector v is equal to 20I minus 5j meters per second. What are the components of the acceleration? B, what is the direction of the acceleration with respect to unit vector I? And C, if the fish maintains constant acceleration, where is it at t equals 25 seconds, and what direction is it moving? Okay, so here's just, here's the fish. And so this is all the vectors that they gave us, velocity initial position, it had it swimming for 20 seconds, it had constant acceleration for 20 seconds, and then this is its velocity after those 20 seconds. So to find the components of the acceleration, we have to find the x component of the acceleration and the y component of the acceleration. So to find the x component of the acceleration, we need the change in the x component of the velocity all over the change in time. And so we can go back to these equations and we can see that the change in the x component of the velocity is 20 from here minus 4 from here meters per second all over 20 seconds. You should get 0.8 meters per second squared. We do the same thing for the y component of the acceleration and you get negative 5 minus 1 meters per second all over 20 seconds, and you should get negative 0.3 meters per second. And now for part B, it is asking for the direction of the acceleration, so we can simply take tangent of theta is equal to the y component of acceleration all over the x component of acceleration, and once you plug everything into that, you should get negative 20.56, or you could say its coterminal angle, which is 339.4 degrees. And then C is asking for the position and direction that it is moving in after 25 seconds if it contains constant acceleration. And so for that, we need to find the position. We can simply find the y component and x components. So you have the position of x is equal to the initial x component of the velocity times t plus half times the x component of acceleration times t squared. And then you also have to add the initial position in order to find the final position, of course, because this equation is just for like the displacement. So then once you plug everything in, you should get 360 meters. Then we'll do the same for the y component of the position. We'll do the initial velocity, the initial y component velocity, times time plus half times the y component of the acceleration times the time squared plus the initial position for the y component. Then once you plug everything in, you should get negative 72.8 meters. And then, so this is what the new vector for the position at 25 seconds. And then in order to find what direction it's moving in, we can use tan theta is equal to the y component of the velocity over the x component of the velocity. But then we don't know these two values at the new time, so we have to use kinematics to solve for those. So we have the final y component of velocity is equal to the initial y component of velocity plus acceleration times plus the y component of the acceleration times t. And so once you plug in everything from there, and for the acceleration, you'll be using the values that we found in part A. So for that, you'll get negative 6.5 meters per second. And then for the x component of the final x component velocity, you set that equal to the initial x component for velocity plus the x component of acceleration times time. Once you plug everything into that, you should get 24 meters per second. And then finally, we can take these two values and plug them into this equation. So once you plug it in, you should get negative 15.2 degrees.